So I guess the first question is, are there questions on stuff we did last week? OK. So last week, you remember, we talked about quantum error correcting codes. I showed you the 9-qubit code and the quantum error correction conditions for general quantum error correcting codes. So this week, I wanted to specialize to a class of quantum error correcting codes that kind of contain the most useful and most well-known codes. They're not going to be all quantum error correcting codes, but they still contain quite a large class that's useful for a lot of purposes. So to get that started, first remember that that last week we showed that it was enough to correct, if you wanted to correct, say, a general t-qubit error, it was enough to correct just Pauli errors on up to t qubits, right? Because they formed the t-qubit Pauli errors formed a basis for the space of 2 to the t by 2 to the t matrices, and therefore you could write any error as a sum of Pauli errors. And the Pauli errors, Pauli matrices, are going to play a really big role today and most of the rest of the course. So let's write down some more properties of them. So of course, we have the identity. We have X. Y, and Z. And so frequently, I'm going to be using not just these things, but also tensor products of them and products of them. So in fact, what I'm interested in is something called the Pauli group, which I'll denote as P sub n. And it's made up of all tensor products of these Pauli matrices on n qubits. And so a group is supposed to be closed under multiplication, right? So certainly tensor factors of I, X, Y, and Z are one set of things, but they can't be the whole group. Because, for instance, if you take X times Z, that's equal to minus Z times X. So in particular, if you take XZ, XZ, you're going to get minus the identity, right? And so that's something that's not in this set that I've written down so far, so we have to include it as well. And similarly, you can get, by involving Y, remember, is I, X times Z, so you can also get I that way. But that's it, actually. If you look at all products of X, Y, and Z, you'll get X, Y, and I, X, Y, and Z, but with an overall phase of plus or minus 1, plus or minus I. So that's what we're going to include in here. And so this group is quite a nice group. It's not a billion, but it's kind of almost a billion. So the only thing that can happen is things commute or anti-commute. And so you have the following nice properties. So first of all, the size of this thing is, well, there's 4 to the n tensor products. And then you have the overall phase, so the size is 4 to the n plus 1. So if you have something in the Pauli group, then its eigenvalues are either plus or minus 1 or plus or minus I. Okay? And so this is the case if you just take the bare Paulis or have minus. So if you have a tensor product with I, X, Y, and Z, or minus a tensor product. And this is the case if you have I times the tensor product or minus I times the tensor product. Okay? So, I mean, this is obvious if you look at Z, and these things are the same, basically. And if you take tensor products, obviously you get products of plus or minus 1. And then, so the more interesting properties, so one I already mentioned, which is if you have two things in the poly group, then either they commute, so if you're a physicist, you would normally write this way, and I might write it that way. So those of you who are not physicists, that's what it means. It means they commute. Or they anti-commute. PQ is equal to minus QP, which, again, physicists write this way. So, so one interesting thing about this property is that, so for the single qubit polys, X, Y, and Z all anti-commute with each other. You can just check that. But if you have two qubit polys, and of course, they commute with themselves, and they commute with the identity. But for two qubit polys, you can have non-trivial commutation. So for instance, X tensor X commutes with Z tensor Z. Why? Because you move X past Z, you get a minus 1. But if you move two X's past two Z's, you get two minus 1s, because it's a plus 1. Okay? So once you're dealing with 2 qubits, 3 qubits, 4 qubits, you have both cases show up in interesting ways. And then finally, the last property I'll be using a lot is that if P is in the poly group, then P squared is equal to plus or minus the identity. And again, the plus case appears when you have just tensor products of I, X, Y, and Z, or minus I, X, Y, and Z. And the minus case is when you have the plus or minus I times the tensor product. Okay? Hopefully that was clear enough. That was not too complicated. So the next thing to do is to go back to the 9-qubit code. And let's try to get kind of a deeper insight into how it works and how we could design other quantum error correcting codes. So let me write it down again. Okay, so you remember for the 9-qubit code, we corrected bit flip errors by looking at sets of 3 and saying, is one of these qubits different than the other two? And in particular, we broke that down into saying, are the first two qubits the same or different? Okay, so if for classical bit strings, you would say that's taking the parity of those first two bits. Are they the same or different? Do they have even number of ones or an odd number of ones? But we want to be more quantum mechanical. So we're going to try to write that as an eigenvalue of some operator. So in particular, we're going to look at tensor products of Z. Okay? And we say, suppose we have 2 bits. If they're the same, 0, 0, or 1, 1, then that's a +1 eigenvector of Z tensor Z. Right? Because if you have 2 zeros, you get 2 +1 eigenvalues for the 2 Z's. And if you have 2 1s, you get 2 -1. And that squares to +1. Okay? Conversely, if they're different, you have 0, 1, or 1, 0, that's a -1 eigenvector of ZZ. Okay? So that means that when I say, should we, I mean, when we're seeing if these first two bits are the same or different in the computational basis, that's saying that we're checking whether it's a +1 or a -1 eigenvalue for Z tensor Z. So basically, we want to measure, for the first bit of the error syndrome, we want to measure z tensor z on the first two qubits. And similarly, to see if the second and third are the same, we measure z tensor z on those two qubits. And so on for the other sets of 3. Okay? So to detect and identify bit flip errors in this code, we're measuring these 6 operators to determine their eigenvalues. Now, the other thing we need to do is correct phase errors. So how do we do that? Well, we want to see if these two phases are the same or different. Okay? So how is that going to look in this same idea of writing it as an eigenvalue of something? Well, how can we kind of pull out this phase for just one set of 3? So for a single bit, we got +1 for 0 and -1 for 1 if we looked at z. But for this 0, 0, 0 plus 1, 1, 1, well, we're going to have to look at x, x, x. Right? So if we do x, 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 that's flipping all 3 bits. And it takes 0, 0, 0 plus 1, 1 to itself. But 0, 0, 0 minus 1, 1, 1, we're switching the two, so we get a -1. Okay? So then if we do x on 6 qubits, in this case, we'll get +1 squared. In this case, we'll get -1 squared. But in either case, it's a +1 eigenvector of this tensor product of 6 x's. Whereas if they were different, if we had a plus and then a minus, because we have an error, then we'd get an eigenvalue of -1. Okay? So that fits in here too. Okay, so here's a set of 8 operators whose eigenvalues give us the error syndrome for this 9-qubit code. Okay? So obviously, what I've written down here, I've omitted the i's. So each row is going to be a separate operator. And really, this is, of course, z. It's a 9-qubit thing. So it's z tensor 7 i's, and so on. Sometimes I'll do that, sometimes I won't. In this case, it seems easier since there's a lot of i's, to avoid them altogether, to avoid cluttering it up. OK, so are there questions about this so far? Yeah?
So like, if we had concatenated like the short code in the opposite order, would we have had the same I guess, operators to check the error syndrome? Would it be like flipped? Like it'd be like pairs of x's, then like 6 z's and 6 z's? And
yeah.
So is there like, does it matter which, like, is there a reason Shor picked this order instead of that other order?
No, I don't think there's a real reason. I guess you'd have to ask him why he did this. It certainly works either way. So this version, I mean, but the codes are not really the same. So this version of the code is a bit better at correcting bit flip errors than phase errors. So it certainly will correct one. If you just have one bit flip and one phase error, either way, it'll correct that. But this one, if you have a bit flip error in the first set of 3 and another bit flip error in the second set of 3, it also can correct that. Right? So there's some cases where you have 2 bit flip errors, and you can correct them. Obviously, if you have 2 in the same set of 3, then you're out of luck. So it doesn't correct all 2-qubit bit flips, but it does correct some. If you do it the other way around, then it's going to be a bit better at correcting phase errors. So I don't know if we're going to have time for it in this course, but there's kind of a version of this code using something called subsystem codes that kind of restores that symmetry between x and z. And you can also think of it as kind of a family of codes that includes these 2 examples as, in some sense, extreme points. The upshot being that this code has kind of some extra room after correcting 1 bit flip error and 1 phase error, has some kind of extra room to determine what else you do in order to make it work. And so you have some options there, and you can, for instance, trade off extra bit flips versus extra phases in that case. OK. Are there other questions? OK. So right. So the next thing to point out is that this set of operators that I wrote down is not really unique. So for instance, I could have said, instead of saying if the first two qubits are the same or different, I could have said, oh, the first and third qubits, are they the same or different? Right? And clearly that would have worked just as well. You know, if the first and third and the second and third are the same, then that means the first and second are the same. And what that means in terms of this is that the first and third, well, we get that by the product of this and this. And that makes sense, right? Because if it's a +1 eigenvector of this and a +1 eigenvector of this, then it'll also be a +1 eigenvector of the product. Right? And in fact, anything that's in the product of these things is going to have a +1 eigenvalue for the valid code words. So really what we're looking at is not this set of 8 operators, but the group generated by these 8 operators. And so let's think about that. Yeah, let's start a new board. So now I'm not going to just be doing the 9-qubit code. I'm going to talk about a general quantum error correcting code. And for this code, probably this deserves to be called definition. So given a quantum error correcting code Q, and in this case I'm referring to Q again as the subspace. I don't really care right now about which set of errors it corrects, or the exact unitary encoding. So the stabilizer is going to be a set S of Q, which is the set of all polys in the n-qubit polygroup such that p psi equals psi for all code words. OK? So this is saying that psi is a +1 eigenvector of p. And remember, I wrote down these 8 operators to be operators that had that property, that they're +1 eigenvectors of all the code words. I mean, I only pointed it out for the logical 0 and for the logical 1. But if it's a +1 eigenvector for all the basis states, it must be for the if all the basis states are +1 eigenvectors, then any superposition will also be a +1 eigenvector. And what I didn't tell you before, but is true, is that if you look at all products of these for the 9-qubit code, that's in fact everything like this that has this property. OK? So these stabilizers have some important properties. So the first one is kind of obvious, but needs to be stated. And that's that minus the identity is not in the stabilizer. Right? So of all the things in the poly group, you'll never get minus I. Why? Well, minus I has no +1 eigenvectors. Okay? So it's never going to satisfy this equation. So the second is that the stabilizer is a group. So why is that? Well, if M and N are in the stabilizer, then Mn applied to psi is, well, N applied to psi is psi by this property. So that's M times psi, and that's equal to psi. So this is saying that psi, if psi is in the code, then psi is again a +1 eigenvector of M times N. Okay? Which implies that Mn is in the stabilizer. Okay? And then the final property is that not only is it a group, it's abelian. So what does abelian mean? It means that everything in the group commutes. So let's again see that. So suppose we have Mn in the stabilizer. We know that Mn psi is equal to psi. And it's also true that Nm psi is equal to psi by the same argument. So Mn minus Nm psi is equal to 0. Okay? But M and N are in the poly group. And in particular, that by this property 3 up there, that means that either M and N commute or they anti-commute. So if they anti-commute, then in that case, Mn minus Nm is equal to, well, Nm is minus Mn if they anti-commute. So this is equal to 2 times Mn, which is 2 times something in the poly group. But anything in the poly group has eigenvalues as non-trivial eigenvalues only, right? It's plus or minus 1, plus or minus I. And here we have this psi has eigenvalue 0. Okay? So this is not a possibility. And therefore, M and N commute. Okay? And that's true for arbitrary M and N in the stabilizer, so that shows it's abelian. Okay? Right. So like I said, in the case of the 9-qubit code, the stabilizer is actually the set of all products of those 8 things there. So they form generators of the group. So note that so in the case of the 9-qubit code, there's these 8 generators. And more generally, suppose we have R generators for a stabilizer, which will be M1 through MR. Well, since it's an abelian group, that means that it doesn't really matter if we want to take the arbitrary element of the stabilizer. There's going to be some product of these things. And it doesn't matter what order we take that product in. So the arbitrary element is going to be of the form M1 to the A1, M2 to the A2, times so on, MR to the AR. And moreover, remember that if P is in the poly group, and all of these M1 through MR are in the poly group, then P squared is equal to plus or minus I. And it can't be minus I because minus I is not in the stabilizer. So that means that that Mi squared is equal to the identity. And so that means that these powers that we take, they can only be 0 and 1. Okay? So what that's saying is that this is a set of all possible elements of a stabilizer, is products of subsets of the generators. And in particular, one thing you can immediately see is that the size of this thing is going to be 2 to the R, right? Because you can go through each possibility of A1 being 0 and 1, A2 being 0 and 1, and so on. Okay? Any questions on this? Okay, so that's great. So given an arbitrary quantum error correcting code, we can define this stabilizer. But why do we really care, right? In the case of the 9-qubit code, it was interesting because we could use it to identify errors. So it turns out that there's a family of codes for which that's a reason to do that. But actually, there's an even better thing for those codes that we can do, which is rather than write out these basis states and then figure out the stabilizer, we can go the other direction. We write down a stabilizer, and then if needed, and generally we don't actually need to, we can figure out what these code words look like in the standard basis. So to do that, so we're going to let S be an abelian group. Maybe I should be consistent about capitalization here. That's a subset of the polygroup, I guess, with the property that minus the identity is not in S. So this S then satisfies those three properties that a stabilizer always satisfies. And it turns out that those are, in fact, not just necessary, but sufficient conditions for S to be the stabilizer of some code. And so in particular, we can write down this code, T of S. So this is going to be a subspace that we're defining. And it's the set of vectors psi such that m psi equals psi for all m in S. Okay? So this is the set of quantum vectors that are +1 eigenstates of everything in the stabilizer. So it's kind of the dual of the definition of stabilizer from the code. Okay? So in this case, T of S is called the code space of S. And so one thing you can see is that if you start with a stabilizer and you take its code space, and then you take the stabilizer of the code space, you just get back to where you started. Okay, that's not immediately obvious, but it's true. Okay, but the converse is not true. So if you start with Q, and you take the stabilizer of it, and then you take the code space again, you might get something that's bigger than Q. Why is that? Well, so certainly it has to include Q, right? Because everything in this stabilizer S of Q is going to have +1 eigenvector. Everything in the code space is going to have +1 eigenvalue for everything in S of Q, right? And so therefore it satisfies this property. But there might be some other vectors that don't, in general. Sorry, that have this property that were not in Q originally. So it could be bigger. And in fact, it's not hard to come up with examples where it is bigger. But if you get back to the same thing, and you do for the 9-qubit code, for instance, and then Q is called the stabilizer code. And so for stabilizer code, it's basically equivalent to define the code via the subspace Q or via the stabilizer S. Right, because if you're given S, you can get the code space this way, and if you're given Q, you can get the stabilizer that way. And you can always go back and forth without adding anything else. Whereas if it's a code that doesn't have this property, then the stabilizer would be kind of under-specifying the code, right? It would be specifying some subspace that's bigger than the code. Okay, so stabilizer codes are what we're going to focus on for most of the course. maybe you'll see some non-stabilizer code somewhere, but certainly most of what we're going to talk about is stabilizer codes. They kind of don't maybe have every property you can think of general codes, but they have kind of most of the important properties. Okay, so let's think about stabilizer codes and what kinds of properties they have. Yeah.
Just a quick question. Like, I was having difficulty trying to find a non-stabilizer code. Do you
Sure.
have like, a really quick example of a non-stabilizer?
Sure. I mean, if you don't care about how good it is at correcting errors, then so we'll have the logical 0 be 0, 0, and the logical 1 be 0, 1 plus 1, 0. That's a non-stabilizer code. How do I know that? Well, I know that because I know a lot about the properties of stabilizer codes, and I know it can't ever look like this. If you don't know those properties, it's not so obvious. But look at it and try to think of something that'll work. So yeah, so there may be, so this, let's see, so there may be, yeah, offhand, I don't even know if there's any single poly that would be in the stabilizer of this. But, oh, actually, no, there can't be. Otherwise it would be a stabilizer code. Yeah, so I think that's the way to see it, is that it's not so easy. But if you look through all the polys, you'll find that none of them has +1 eigenvalue for both of these two things. Are there other questions? Yeah.
So for every code that has a stabilizer group, does it uniquely define a stabilizer code, like that set of stabilizers?
Yeah, so the group defines the stabilizer code uniquely. The set of generators is not unique for that group, right? So that's what I already mentioned, that you could take different products. And in fact, one of the assignments on the problem, problem number 2 is to think about different generating sets. Yeah.
So if you have, does each generator split, like say you're dealing with like P3, so you have like, whatever that, like, does each generator cut the number of polys possible in half, or sorry, the number of code words in half?
Yes, okay, in fact, that was exactly the next thing I was going to do. So maybe I should ask if there's more questions on this before I do that. Right, okay, so yeah, so it's very natural to say, okay, so we've defined a code via its stabilizer. How big is that subspace, right? And it's true, each poly has eigenvalues. So we're only in the case where they have eigenvalues plus and minus 1. And so each one is going to split the whole Hilbert space into a half that has eigenvalue +1 and a half that has eigenvalue -1. I guess I didn't write down that you actually are dividing the Hilbert space in half, but it's true. But then you have to say, well, what happens if we pick a different one, a second one? Is it also subdividing those two things in half again, right? And in fact, it does. And so that's kind of the thing that you can remember, that every time you're picking a new generator, you're dividing the Hilbert space in half. So if you started with an n-qubit Hilbert space of dimension 2 to the n, now let me write this down in the theorem. So if the dimension of the code space is going to be some power of 2, where k is n minus r, r generators for S. Okay, so we started with a Hilbert space of dimension 2 to the n, and every time we pick a generator, we're dividing it in half. So the total dimension that we're left with is 2 to the n minus r. But in order to prove that, you'd have to see that every time you're picking a new generator, you're actually not just dividing the whole Hilbert space in half, but dividing the subspace that you have left in half. Okay, and so that's a little less obvious. So let's take the projector onto the code space. So that's going to be, I claim, this. It's the sum over all elements of the stabilizer. And then the normalization factor is 1 over 2 to the r. So remember, there's 2 to the r elements in the stabilizer. So why is this projector? Well, suppose you have psi in the code. Sorry, how am I defining it? I'm defining it the other way. And I apply this projector to it. I should get the same thing again, right? So let's do that. Sorry, is this defined the right way? Yeah, OK. So suppose psi is in the code, and I apply the projector. So then PS psi is equal to 1 over 2 to the r, sum of m psi. And m psi is equal to psi, because psi is in the code and m is in the stabilizer. So this is equal to, well, there's 2 to the r terms here. And so we get sum over psi 2 to the r times, and there's a 1 factor of 2 to the r, so this is back to psi. OK? So that means that pi_vest applied to a code word actually does give you a code word. Now, suppose it's code word. So now we also have to ask, what if how do we know that pi_vest doesn't project to something bigger than the code space? Well, what we can do is we can take m in the stabilizer and apply it to something of this form, where psi is arbitrary. Now, it doesn't have to be in the code. So m times this is equal to 1 over 2 to the r, sum, here, let's do this n. Sum over m in the stabilizer, n times m, psi. But what have I done here? And if m is in the group, and n is in the group, then n times m is also in the group, right? And moreover, n times m cannot be equal to n times m prime unless m is equal to m prime. So this is in the group, and for different values of m, it's a different element of the group. So before I had the sum over everything in the group, I still have the sum over everything in the group. I've just rearranged the terms. OK? So this is equal to sum over m tilde in S psi, which is then back to this projector. OK? So this is saying that pi s psi has this property that for any n in S, it has a +1 eigenvalue. So that implies that pi s psi is in the code space. OK? So this shows that pi_vest is actually the projector onto the code space. OK? So everyone got that? And so then I can find the dimension of the code space by taking the trace of pi s. So pi s in the appropriate basis is a bunch of 1s along the diagonal and then 0s. And there's a 1 for each dimension in the code space. So the trace of ps is equal to dimension of the code space. And so we can do that by taking the trace here. So it's 1 over 2 to the r, sum over m and s, trace of m. Now, this is a property I didn't write down, but the trace, if you have a non-trivial Pauli, the trace of it is 0. Right? Certainly for x, y, and z, you can see that immediately. But of course, the trace of I is not 0. And so what that means is that for everything in the stabilizer that's not the identity, this trace gives us nothing. So all that's left, and the identity has to be in the stabilizer, right? Because certainly it's a plus, it has +1 eigenvalue for everything, at least for the code words. And so we get the trace of the identity over 2 to the r. Trace of the identity is 2 to the n. And so this is 2 to the n minus r, which is the theorem. OK? Any questions on that? Yeah.
It's sort of continuation of the same question. It makes sense that the stabilizer will cut the space in half, but how do I know how can I make sure subsequent stabilizers are going to cut it in half orthogonally? Like if I have my space, I cut it in half. And
I just proved it.
That proves that.
Yeah. Certainly it. Yeah, because it says that if you take, so you can form a stabilizer by any so if you take any group that has those 3 properties, right? Well, group is one of the properties. So if it's an abelian group that doesn't include -1, then it can be a stabilizer of something. And so in particular, if you start to pick generators that commute with each other, and then look at the group generated by those things, that gives you a stabilizer that has these properties. And therefore, this theorem applies. And so that means that every time you're picking another generator, you could take an existing one and add a new thing that commutes with it, right? And so then the dimension went down from 2 to the n minus r to 2 to the n minus r minus 1, right? So you really have cut it in half again. Okay. Okay. So this is one of the basic properties of stabilizer codes. The number of logical states is a power of 2. So you have k logical qubits. So that's a nice thing. And the next thing is, but this is kind of in some sense, a very basic property. What we're really interested in is the ability to correct errors. And it turns out that looking at the stabilizer can do that, which you already kind of saw from the that's useless. Okay. Which we already saw from the 9-qubit code case, but it is more general. So how does that work? So for the 9-qubit code, we're using the Z operators here to identify bit flip errors. And we're using the X operators to identify phase errors. So that's kind of the general thing that we're going to be doing. We're going to be using some of the Pauli operators to identify errors of different kinds. And in particular, the property that really matters is whether the error commutes or anti-commutes with an element of the stabilizer. So, so suppose we have a stabilizer code, and suppose we have an error and we have some element of the stabilizer such that E and M anti-commute. Well, so originally we had psi in the code space. And then E psi, we want to see if this is still in the code space or not. Okay? And in particular, we want to see if it has +1 or -1 eigenvalue for M. So let's apply M to it and see what happens. Well, ME is equal to -EM because they anti-commute. And M psi, since psi m is in the stabilizer and psi is in the code, that means that m psi is equal to psi. So this is equal to minus E psi. So what this is saying is that m E psi is equal to minus E psi. So in other words, E psi is a -1 eigenvector of m. Okay? So this error E that anti-commuted with m took us from a +1 eigenvector to a -1 eigenvector. And on the other hand, if E and m commute, then we can do the same thing. We say, oh, m E psi is equal to E m psi, and m psi is equal to psi, so this is equal to E psi. So E psi is a +1 eigenvector. Okay? And so this is the basic property that lets us identify errors. We can look to see, so we start out with a state that's all +1 eigenvectors for things in the stabilizer. And then some error happens, and then we measure the eigenvalues. Okay? And if some of the eigenvalues have changed to -1, that means we know that there's been an error. And moreover, we have some information about what error it is, because it is something that commuted with the things that are still +1 and anti-commuted with the things that are -1. Okay, so in particular, what we're seeing here is that M detects errors that anti-commute with it. And so that suggests we define the set of things that commute with everything. That's clearly going to have some spectral properties. So we're going to let n of s be the set of polys such that m and n commute for all m in the stabilizer. Okay, and so anything outside of n of s can be detected by this code, right? Because that means that there's some generator in the stabilizer that will detect it. But it turns out that the set of undetectable errors So anything outside n of s is detectable, definitely. Anything in n of s, well, when we measure the eigenvalues, we'll always get +1s. And so we'll think that an error has not happened. Okay? And if there actually was an error, that's a problem. But the thing is that there might be some things that actually didn't change the code. Right? And so in particular, note that the stabilizer itself is always a subset of n of s. Right? Because the stabilizer is abelian. So everything in the stabilizer commutes with everything else in the stabilizer. And therefore, it satisfies this property. Okay? And if you have an error that's in the stabilizer, well, it's not really an error, right? Because if it's in the stabilizer, it takes code words to themselves, right? That's how the code and the stabilizer are defined. Okay? So really, it just acts like the identity on the code. And what that means is that if you have something that's in n of s, but it's in s, then that's not a problem. So it's only the things that are in n of s but are not in s that are a problem. And anything that fits in that category definitely is a problem. Why is that? Well, it's something where measuring the eigenvalues of the code doesn't help you. Okay? And in particular, following this, that means that you start with a code word, you still have a code word, right? Because it's a +1 eigenvector of everything in the stabilizer, which means that it satisfies this definition of the code space, wherever it is. Here it is. But this is something that's not in the stabilizer, right? Which means that it doesn't have the property that it fixes all the code words. So there must be some code word it takes to something different. And in particular, it has to be a different code word. Okay? So that's an error that mixes up things in the code, but that we won't be able to detect because we don't know which code word we started with. Okay? So these are the set of bad things that could happen, things that could happen and we'd have no way of knowing that the code word had actually changed. Okay? Okay, so, but now suppose we want to correct errors. So this is detecting errors. And so if two errors have different error synchromes, so they commute, well, if they have different error synchromes, then we'll be able to tell them apart, right? And so if we can tell all the errors apart, then we can tell which one happened, then we can correct it. That's not a problem. So how do we know when two things have different error synchromes? Well, they have different error synchromes if they commute with the same elements of S, right? Because the error synchrome is the set of eigenvalues of the generators of the stabilizer. And if E and F commute with the same elements of F, so they might commute with some elements and anti-commute with other elements, but it's both the same. And so that means if you take the product E dagger F, which remember showed up in the quantum error correction conditions, well, since E and F commute with some elements of F and they commute with the same elements of F, that means that of S. So if you have M that commutes with E, it also commutes with F, and so this product commutes with it. And if you have M that anti-commutes with E, it also anti-commutes with F, and therefore this product again commutes with it. So that means that E dagger F commutes with everything in the stabilizer, which is equivalent to saying that E dagger F is in N of S. Whoops. Okay. So this is a sufficient condition for error correction that E and F always have different error synchromes, and so it's sufficient if E dagger F is always outside N of S. Sorry, this is wrong. This is have the same error synchrome. Okay, so sufficient condition is if E dagger F is always outside N of S. But this undetectable part has this minus S in it, which should tip you off that there's also a little bit more for error correction. In particular, let's think about that case when E dagger F is in S. Okay. So suppose E dagger F is in S. Well, then that implies that for all code word psi, E dagger F psi is equal to psi. And multiplying by E on both sides, we get that E psi is equal to F psi for all code words. So in this case, E and F act exactly the same on code words. We can't distinguish them by the error synchrome, but we don't need to because they're basically the same error. Okay? So that's also an acceptable possibility. And so that leads us to the main theorem of stabilizer codes. So a stabilizer code defined by the stabilizer S can correct a set E of errors, which is a set of Pauli errors, if and only if E dagger F is never in N of S minus S. Yeah, okay. So I showed you one direction of this. Basically, I said that if E and F, if E dagger F is always outside N of S minus S, then you'll have some sets that have the same error syndrome but actually act the same. Then it's a degenerate code. And you'll have some cases where the errors have different error syndromes, and you can distinguish them. So now the other direction is saying, suppose we have some case where E dagger F is in N of S minus S. And by almost the same argument that I gave before, that's going to be a problem. Why? Well, it means that that E and F have the same error syndrome, so we can't distinguish them with the code. But they do different things to the code. This is not the case, right? Because if they do the same thing to all code words, the product is in the stabilizer. Since it's not, there must be some code word where they do different things. Okay? But nevertheless, we can't tell them apart by just measuring the error syndrome, which is really all the information we have about the code. Okay? So, so that's why this works both ways. Yeah, and if you wanted, you could also just plug it into the quantum error correction conditions and show it that way. That works too. Okay, and so what that means is that if we have a stabilizer code, you can read off the distance from the stabilizer without ever having to write down the code words in the basis state and work out stuff like that. So in particular, the distance of a stabilizer code S is the minimum weight of an element of this undetectable set. And the code is degenerate with respect to lowest weight errors if this is also the minimum, sorry, if this is not, yeah, let me write it differently. Must be erased somewhere. So it's degenerate if S contains an element of lower weight. Right, because in that case, you have some relatively low weight products in the stabilizer. So you have this property holding true, where you have two low weight errors that do the same things with code words. These are two correctable errors. Right, and so that's a case where if you applied the quantum error correction conditions, you would see that the matrix rank can't be maximal because these two errors give you the same thing, right? They won't be orthogonal. They'll be the same. And so E minus F is giving you 0 on the code words. OK. And so then some notation. So so remember, for general quantum error correcting codes, we had this double parentheses notation. So for stabilizer codes, it's a little more specialized. So in the general case, we were always we were generally focusing on n qubits, and we're still doing that. But before, the dimension of the code space didn't have to be a power of 2, right? So we didn't have to have an integral number of logical qubits. In this case, we do, right? So we can bring that out. And we'd like to emphasize that it's a stabilizer code, not just a general quantum error correcting code. So for a stabilizer code, so if we have n physical qubits, k logical qubits, and distance d, we say it is square brackets nkd code. Yeah.
Just a quick question on the correlation.
Sorry, on which one?
The second part. The code is degenerate if
Correlate.
it contains an element of lower weight. Then which weight? The minimum?
Then the distance, let's say.
Oh.
Which is also the minimum weight of something in n of s minus s. So the point is that if it's non-degenerate, then it's enough just to look at the weight of things in n of s, right? But if it's degenerate, then there'll be some low-weight things in n of s, but they'll also be in s.
Okay, yeah.
Okay? Other questions? Okay, so so now I want to use yeah. Okay, I guess there's one more thing I want to say. Well, okay, let me give the example first. So let's use this formalism to come up with another quantum error correcting code that's better than the 9-qubit code. So let me write down an appropriate stabilizer. So it's going to involve 5 physical qubits. This is a 5-qubit code. So in this case, I'm omitting the tensor product factors, and I am putting in the i's, because there's not too many of them. And so you see 5 physical qubits. Each row is 1 generator. And so there's 4 generators, 5 physical qubits. So, well, OK. So the first thing to check is that it's an abelian group. But if you check, you'll see that it is. So for instance, this and this commute, because we have one place we have a z and x, and another place we have a z and x. So they commute, and so on. And so, so this code has 5 physical qubits and 4 generators, so it has 1 logical qubit. And what's less obvious is that it has distance 3, and in fact, it's non-degenerate. So one way of seeing that is to kind of look through all of the yeah, so there's a couple of ways of seeing it. So one way is to look through all of the 2-qubit errors and see that, all of the 1 and 2-qubit errors and seeing that they all anti-commute with something in the stabilizer. Another way is to look at all the 1-qubit errors and see that they all have different error synchroms. Okay? And then there's a couple of other ways to kind of derive this more quickly, which I may or may not get to. Anyway, the upshot is that this is a code where for any single qubit error, you get a unique error synchrome. And in fact, that's all there is here, right? So there's 5 qubits and 3 errors that can happen to each qubit, and then plus identity. So there's 16 possible errors. And how many possible error synchroms are there? Well, each of these eigenvalues could be plus or minus 1. So there's 16 possible error synchroms. So in fact, we use up all the error synchroms in doing this. And this turns out to be the smallest possible quantum error correcting code to correct 1 error on qubit. Well, yeah, in general. Okay? It has some other nice properties. For instance, it's cyclic. That's why it was easy for me to write it down. I just had to remember 1 generator, and everything else was a cyclic shift from that. So the last cyclic shift would give you ZZXIX. So that turns out to be the product of all 4 of these things. So it's in the stabilizer. Okay. So the next thing I want to do is talk a little bit about the part of the code that I've been leaving out. So remember, last week I actually defined the quantum error correcting code as a unitary encoding map and a set of errors to be corrected. And this week I've just so far been dealing with it as the subspace. So what about, exactly what the logical 0 is and exactly what the logical 1 is? How do I represent that in here? And so it turns out, so this set n of s minus s is a set of things that do non-trivial gates, non-trivial polys to the code words, right? I said that already. And in fact, it turns out that n of s basically gives you the logical poly group. So in particular, suppose we have n and n prime in n of s. But n prime is just equal to n times m, where m is in the stabilizer. Okay? Well then, n prime times code words is equal to nm times code words, which is equal to, if psi is in the code, then m psi is equal to psi, so this is just equal to n psi. So these two operators differ by an element of the stabilizer, and that means that they do the same thing on code words. Okay? So n and n prime are basically equivalent logical operators in that case. So what we should really be looking at is this quotient group, n of s mod s. And I guess I don't want to go into details, but it turns out that, so it turns out that n of s mod s is isomorphic to the poly group on k qubits, which remember is n minus the number of generators. And so we can interpret these, and each one, remember, is a logical operation. Each element of each coset here defines a logical operation. And so we can think of this as the logical polygroup. And choosing how it acts as a logical polygroup is equivalent to choosing what the logical 0 and the logical 1 are for this code. Okay? Why is that? Well, the logical 0 is the +1. Suppose you have just one logical qubit. The logical 0 is the +1 eigenvector of the logical z operator. And the logical 1 is the -1 eigenvector of the logical z operator. Okay? And we can really choose any way. I mean, there's many possible ways you could do this. And so that's some ambiguity of going from the code space as a subspace to the actual encoding map. But that's an ambiguity that really exists in this code. The thing is that doing this is not going to change the error correction properties at all. I mentioned that last week. But it might change some other properties that you might be interested in about this code. So you can choose one that's convenient. So for the 5-qubit code, frequently we choose the logical x to be the coset represented by the tensor product of 5 x's, and the logical z to be z, 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 z on 5 qubits. Z, 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 z. And you can check that these two things actually commute with everything in the stabilizer. And since there's one logical qubit, these kind of generate the logical polygroup. It's enough to just look at them. Okay? So are there any questions on this part so far? Okay, so this is one example of a code, but I just kind of threw it at you out of nowhere. It turns out it's not actually very hard to come up with an equivalent 5-qubit code. If you just say, okay, there's 16 possible error syndromes. Let me just try to make, assign them to the single qubit errors in such a way that all the single qubit errors have different error syndromes. Let's try to do this in some way that's consistent and come up with a 5-qubit code. You can sit down and do this by hand, and you'll come up with a 5-qubit code. But we'd like more systematic ways of deriving them. So the next thing I want to do is talk about a couple of different ways of getting stabilizer codes, but deriving them from kind of known classical error-correcting codes, or in some cases unknown classical error-correcting codes that you might come up with. But before we do that, I think this is a good time to take a break. And so let's come back in 10 minutes, and we'll start with CSS codes. So to start, are there questions from the first half? Or last week or anything? What did I do with this? OK. No questions? OK, so like I said, now I want to talk about how to derive stabilizer codes from classical error-correcting codes. So to do that, I have to talk a little bit about classical error-correcting codes. So in particular, I'm going to focus on a class of codes called linear codes, which it turns out are basically a subset of stabilizer codes, if you think of them the right way. And so in particular, so classically, instead of quantum states, we're dealing with bit strings. And a classical code classical code is just some set of bit strings. Now, this is in much the same sense that a quantum error-correcting code is a subspace of the Hilbert space. So you don't just want any set of bit strings. You want a set of bit strings that has nice properties that make it a good error-correcting code. But I'm going to focus on a subset of classical codes. I mean, you can derive theory for general classical codes, but we say that this code is a linear code if it has the property that whenever x and y are vectors in C, then x plus y is in C as well. Okay? What this means is that the code itself is actually, you can think of it as a binary vector space. That's a subspace of the binary vector space of all n-bit vectors. So we can define a linear code via what's called the generator matrix. Which is a k by n binary matrix. Basically, each row is a code word, is a kind of basis code word. And then the general code word given some logical vector bit string v that we want to encode, it's encoded as G transpose V. So V is a logical thing, so it has K. K is the number of logical bits here. And N, of course, is the number of physical bits. So V is a k-bit string, so a vector of length k. And so when we take G transpose V, we're getting something of length n. And that's going to be the code word. So one example that we'll be working on is the Hamming code, the 7-bit Hamming code. Let me spread this out a little bit more. Make it more easy to see. Okay. So for instance, this linear code, well, it contains the all zeros vector, because you can get that from V being all zeros and applying G. It contains this vector, all ones, contains this vector, contains the sum of this and this, which you could get from 0, 1, 1, 0. Okay? So basically, you can think of just adding up some subset of rows of this matrix and getting all the code words. Okay. And then so the Hamming distance between 2-bit strings is the number of places where they differ. right? So for instance, the Hamming distance between this and this is 3, because they differ in these last 3 places. And the Hamming distance between this and this is 4, because they differ here, 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 and here. And then we say the distance of linear code C is the minimum Hamming distance, minimum between any pair of code words. And so using notation, so then we say the code has n physical bits, a linear code with n physical bits, k logical bits, and distance d is nkd code. So it's basically the same kind of terminology as we did for stabilizer codes, but with single brackets instead of double brackets. And of course, the quantum terminology was used in imitation. And so if you have a general code, general classical code, you would do it with single parentheses and have this, where k is the number of logical states, not the number of logical bits. Again, like in the stabilizer case. So I mean, so this is one way. This is, for me, the easiest way of thinking about Hamming distance. But another way of thinking about it is if you take the bitwise XOR of 2 bit strings. So that's basically addition as vectors, binary vectors, mod 2. Then the Hamming distance between those 2 bit strings is, if you take that sum, what's the number of places the resulting thing is non-zero. Right, so it's the weight of the sum. So because the linear code has this property that it's closed under sum as binary vectors, then that means that the sum is also a code word, right? So that means for linear code, yeah, I'm sorry, I guess, right, okay, so actually, sorry. So this definition of distance didn't even depend on being a linear code. Right, so this distance is fine. But for linear code, the distance is also equal to the lowest weight non-trivial code word. So non-trivial because the all zeros word is always in a linear code. But if you have the shortest thing that's not all zeros, the weight of that is also the distance of the code for a linear code. Okay? Simply by this, right? This property that that x plus y is sorry. X plus y is in the code. Okay, so then the last thing I want to say about linear codes before putting the connection to stabilizer codes is to talk about the parity check matrix. So the parity check matrix is not actually unique, so it could be maybe a parity check matrix. It's a matrix of maximal rank that has this property. So I'm going to write this as H, whereas the generator matrix was G. And so given the generator matrix G, the parity check matrix has this property that HG transpose equals 0. Okay? And the upshot of this is that suppose you have some arbitrary code word, G transpose V, and then you apply H to it. Well, you get 0. Right? Because HG transpose is already 0. So you can think of the parity check matrix. Well, okay. So the upshot is that parity check matrix is kind of a set of constraints on the valid code words. That if you apply H to the code word, you should get 0, right? And if you think of each row of the parity check matrix, sorry, each column of the parity check, each row of the parity check matrix, it's basically a separate constraint. Okay? Whereas you have some vector and you take its dot product, binary dot product, with the code word, and you get 0. And what that's saying is, since the binary dot product is that everywhere you have a 1, you're adding up that element to the code word. And where you have 0, you're not. So you're looking at some subset of the bits in this bit string, and you're adding them up. And it's binary, so if there's an even number of 1s there, you get 0, and if it's an odd number, you don't. So that's why it's the parity check matrix. You're checking the parity of different subsets. Each row gives you a different subset of the bits to check the parity of. And the code words have to have 0 parity for them. So that may sound like what we're doing with the stabilizer, right? And in fact, it is. So the upshot is that you can do kind of the same thing with the parity check matrices as you did with stabilizers. You can look at the error synchrome. So suppose suppose classically we have some error E. So there's some set of bits that are flipped. Okay, we can also represent that as a bit string with a 1 in the bits that are being flipped. And so we started with code word X, and it goes to X plus E, right? And that flips the bits in the places where E is 1. And then suppose we apply H to that. Well, H of X, so by, this is linear algebra. This is a matrix. So H of X plus E is H of X plus H of HE. And HX is equal to 0. So this is just HE. So by applying the parity check matrix to something, we can kind of eliminate the code word, which, well, we care about, but not what we're interested in right now. We're interested in the error. And this gives us some information about the error. This is the error synchrome. So back in our example, so for the Hamming code, the parity check matrix is this. So for instance, this is saying that for all the code words of the Hamming code, the first 4 bits have to have even parity. And these 4 bits, 1, 2, 5, 6, also have even parity. And then to think of how this works with errors, well, we apply it to different error vectors, right? And so suppose we have an error that's just affecting 1 bit, right? So it's 1 in the ith place and 0 elsewhere. 0, 0, 1, 0, 0, 0. Well, what does that do when we multiply here? It picks out the ith column of this parity check matrix. Okay, and so using this property, you can immediately see that all 7 single-bit errors have different error syndromes for this Hamming code, right? Because all the columns here are different. And so that means that this code can correct arbitrary single-bit errors. It has distance at least 3. Turns out to be exactly 3. So the Hamming code, using that notation, is a 7, so 7 physical bits, 4 logical bits, because there's 4 rows to this generator matrix, and it's a distance 3 code. Okay, so yeah, maybe I should stop here to see if there's any questions. This is what I wanted to say just about purely classical error correcting codes. No questions? Okay, so again, these parity check matrices, they do sound really similar to stabilizers, and in fact, that's exactly what they are. So suppose you were just interested in a code to correct bit flip errors, okay? And what you did was you'd say, well, I have these perfectly good classical error correcting codes, right? I have a linear code, and what I want to do is I want to make it into a quantum code. Well, this says, the classical code says the first 4 bits should have even parity. And quantumly, remember, that corresponds to looking for the +1 eigenvector of the tensor product of z on the first 4 bits. Here, maybe I'll write it here. So what we would do is we would get a stabilizer that was z, 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 I, right? And so this thing is basically the same as this constraint here, right? And similarly, we can change the 1s in the second row to z's to get z, z, I, z, z, I. And this is z, I, z, I, z, I, z, okay? And so this is a quantum code. We know it could be able to correct bit flip errors, right? Because the classical code did. It's the code words of this code are basically just superpositions of all the classical code words. Okay? The basis code words are just the same. You put kets around them, but otherwise they're the same. Okay? And we know by carrying this over that it has to correct a single bit flip error, right? Because a bit flip, what is this error syndrome going to be? It's going to be the set of things that anti-commute with that bit flip, right? So the set of, whenever we have a z, it's going to anti-commute. And whenever we have an I, it's going to commute. So for like a single bit flip error, we're taking one column here, which is exactly what we did there to get the error syndrome. Okay? Okay. So the next step, though, is to come up with codes that can correct more than just bit flip errors, right? Well, think about this. So we can recap what we did in the first lecture. We said, well, we have this classical repetition code, which, by the way, is a linear code, and we can convert it into a quantum code that corrects bit flip errors. Similarly, we can convert, say, this Hamming code into a quantum code to correct phase errors, right? How do we do that? Well, it's just the same thing, but with x's instead of z's. So if we took this and we wrote x's here, we would get a code that could correct one phase error. Okay. So now comes the new part. So now suppose we want to get a code that corrects both bit flip and phase errors. So last time we kind of combined two of these 3-qubit codes in a weird way. This time we're going to combine them in a different way. So this is a construction called the CSS construction. So CSS codes. So these are people's names. So it's Calderbank, Shor, Steen. Because this construction was invented kind of simultaneously by Andy Steen and by Calderbank and Shor. And so what we do is we take two classical codes, classical linear codes, C1 and C2. And so for C1, the parity check matrix, so C1 will have parity check matrix H1. C2 has parity check matrix H2. And here we convert to stabilizer generators by taking 1 to Z. And here we convert 1 into X. Okay? And then we put them all together into one stabilizer. So for instance, for the Hamming code, so if C1 and C2 are both the Hamming code, what would we get out of this? Well, we'd get the following thing. So we have the things that I wrote down there. But we also have the same things where I've converted the 1s to x's. Right? Okay. So how do we feel about this construction? What's it going to do? So first of all, the question you might ask is how many logical qubits are there, for instance? So what's the answer? 1. Okay, so why do you say that?
There's 6 generators.
Right, right. But here's the thing. How do we know this is going to have any logical qubits? In order to have, for that to apply, it has to be an abelian group. Right? Is this an abelian group? Well, this thing here was definitely an abelian group, right? It just involves z's. And the part down here just involves x's, so that's definitely fine. But we should check that these things up here commute with these things down here. That doesn't have to be true. Okay? In this case, it is true. Okay? So it is an abelian group. And there are 6 generators, so there should be 1 logical qubit. Now, what's the distance of this code going to be? Well, one way you could just try all single qubit polys and see if they have different error syndromes. But you don't have to. There's a faster thing you can do. you can say, well, this first part is already enough to identify uniquely any bit flip error. So X is taken care of. And this bottom part here is enough to identify uniquely any Z error. So Z is taken care of. And Y is a product of X and Z. So we're going to identify it both on the top and the bottom. We're going to identify the X part on the top and the Z part on the bottom. Okay? So clearly, this code can correct arbitrary single qubit errors. So we know immediately that it's a distance 3 code. I guess it could, in principle, be a higher distance. I'll get to that in a minute. But it doesn't. It's not very likely in general, right? In this particular case, it's not. Right. So there's another CSS code that we've already seen, in fact, which is the 9-qubit code. Do I still have the stabilizer up? Yes, I do. OK. So up there, you see we had two classical codes, right? We had the Z1 and the X1. Now, the thing is, the Z1 is just 3 copies of the repetition code. So we knew that part. That was good at correcting bit flip errors. But in the X part, if we write that down as a classical linear code, it's really a pretty lousy one. Right? The parity check matrix is 6 ones and then 3 zeros and then 3 zeros and 6 ones. And you see it's not good at correcting one error because you have columns that are the same. Right? You have 1 0, 1 0, 1 0, 1 1 1, 0 1 0 1 0 1. Okay? It can't distinguish between, well, in this case, phase errors on the first and second qubits, second and third qubits, and so on. But the quantum code still has distance 3. Right? So that's the case. So this argument that I gave you here says that the distance here has to be at least as much as the distance of C1 or C2. Right? If it's good at correcting bit flip errors and good at correcting phase errors, it has to be at least that good at correcting arbitrary things. But this 9-qubit code is showing you that it can actually be better. And the reason it can be better is because of degeneracy. Right? Because in the classical case, it really mattered that we couldn't tell the difference between, well, in this case, a Z error on the first qubit and second qubit. But in the quantum case, those two errors do the same thing. Right? So if we just had the bottom 2 generators, that would not be a degenerate code. That would be a lousy code, even for correcting phase errors. But with the things on top, the phase errors all kind of wash out. The ones that we can't distinguish are the same. Okay? So the upshot is if we do the general version of this condition, okay, so what we're going to do yeah, okay, I got a little bit ahead of myself. Okay, so we want to make this construction with 2 classical codes. But as I pointed out for the 7-qubit code, we need to check that they're abelian. Right? The resulting stabilizer is abelian. So that's some kind of compatibility condition between C1 and C2. And so in particular, what does it mean? So if we have a row here of the parity check matrix H2 and a row here from H1, we want those two things to commute, which means that we want the number of places. So the first one we have Z's where the 1s were, and the second one we have X's where the 1s were. So we have this vector that's a row of H1 and a vector that's a row of H2, and we want the places where they both have 1 to be even, right? Which is saying that it's the dot product. So we have some row V of H1 and row W of H2. And so the parity of the number of places where they overlap, where they both have 1, is V dot W. Okay, and so that means that the corresponding elements of the polygroup commute if and only if V dot W is equal to 0. Okay? And so what that tells us is we want to look at codes that have this property between the parity check matrices, which turns out to be related to the classical notion of a dual code. So C is a linear code, and then C perp is the dual code. Which is defined as the set of vectors x such that x dot z is equal to 0 for all z in C. Okay? So it's exactly a set of vectors that have this property. Okay? So what we're saying is that and so the other fact is that the parity check matrix of C is a generator matrix for the dual code. Okay, and you can get that by this definition of the parity check matrix, right? Again, you see that it's defined as this maximal thing that has this property that dot products with the generator matrix give you 0. And vice versa. So in particular, C perp is equal to C. Okay, so this means that that C1 and C2 are compatible in the sense that we can combine them into a stabilizer. So if rows of the parity check matrix of C1, which means that they're rows of the generator matrix of C1, rows of H1, which are equal to rows of So rows of the generator matrix of the dual code. So that's elements of the dual code. So if you have elements of the dual code, have to be inside the dual code for C. For C2. Is that right? Yeah, okay, let me try this again. Okay. I mean, this is going to be the right condition. So we have some x that's a row of the parity check matrix for C1, right? Which, as I was just saying, means that x is an element of the dual code for C1. And z is a row of the parity check matrix for C2. So z is an element of C2 perp. And whenever that's true, we want x dot z is equal to 0. Okay? And so what this is saying is that x is an element of C2 perp, which is equal to C2. Okay? Which implies that C1 perp has to be a subset of C2. And equivalently, actually, C2 perp is a subset of C1. Okay? Now I've gotten that right. So are there questions on this part? I know I was a little confusing about how I presented that. Okay, so let me co-op this. Okay, so this gives us our theorem about CSS codes. So let's say we have two CSS codes, two classical linear codes with C1 perp a subset of C2. And let's suppose that C1 is an N K1 D1 code, and C2 is an N K2 D2 code. Okay? So then there exists a quantum code, which is the CSS code, which combines these two codes into the stabilizer in the way that I've been telling you. And it's going to have the following parameters. So the number of physical qubits is the same as the number of physical bits in those two codes. So n is the same. And k, as we'll see in a minute, is going to be k1 plus k2 minus n. Then I'll have some distance d with d greater than or equal to the minimum of d1, d2. Okay. So let me first say about the distance. Well, I kind of gave you that argument already, a little bit prematurely. So the distance, the code is able to detect bit flip errors of up to weight d minus 1, definitely, right? C1 does that. And it's able to detect phase flip errors up to weight d2 minus 1. C2 does that, right? And if you have some arbitrary poly up to weight the minimum of d1 minus d2, well, you can break it down into some number of bit flip errors that's less than that, less than or equal to that, and some number of phase flip errors, also less than or equal to that. And each of those will be detected. Okay? So, in fact, if you want to think of it as a non-degenerate code, the distance will be exactly this. But then the 9-qubit code showed you that there was an example where the true distance of the quantum code could actually be higher than that by taking advantage of degeneracy. Okay? And that's where you get the greater than part of this greater than or equal to. Okay? And so then the other thing to do is to figure out how do we get this number of logical qubits. And that's, of course, just a straightforward exercise. We say, so this is going to be k. So we know that k is supposed to be n minus the number of generators. Well, some generators come from C1, and some generators come from C2. So how many generators come from C1? Well, the generator matrix for C1 has k rows. And so the parity check matrix has to have n minus k rows, right? Because by linear algebra, you have k things, and you want to take the dot product and get 0. And so that's k linear equations in n bits. And so there must be, the solution space must be an n minus k dimensional thing. So there's n minus k 1 rows for the parity check matrix for H1, and that gives us n minus k1 generators as stabilizer. And similarly, we get n minus k2 generators from C2. And putting this together, what do we get? We get exactly this, k1 plus k2 minus n. Okay? Okay, so that's CSS codes from the stabilizer perspective. But suppose you are not that comfortable with stabilizers yet, and you want to go back to dealing with representation in terms of the standard basis. So how do you do that? And this, by the way, is maybe a good exercise for understanding how they relate for more general stabilizer codes as well. So remember that we had this projector onto the code space, which up to normalization just looked like this. Sorry. A sum over everything in the stabilizer. Well, what we can do is we can factor this out. We can factor into a product of some of stuff in the x part of the stabilizer and stuff in the z part. So here Sx is the subgroup of the stabilizer that's generated by things that have x's in them, and Sz is the subgroup that's generated by things that have z's in them. Okay? And this will still give us, this is equal because kind of the arbitrary element of the stabilizer is going to be a product of generators, right? Some from the top and some from the bottom. So it's going to be a product of some x thing and a z thing. And if we expand this out, we'll get all possible products of x things and z things. Okay? And so looking at this projector, so this part says that we should restrict our attention to basis vectors that, well, okay. So this, remember, is the projector onto the stabilizer code that's just from Sz, which was the parity check matrix for the code C1. So this is telling us that all the basis vectors we're going to use, all the vectors that we're going to use, all the kets that we're going to use, basically are code words of C1. And then what is this telling us? Well, this is telling us that suppose we have some such basis code word. Well, it's not enough to just stick with a single ket. We're going to have to apply various products of x's to it, right? And which products do we have? Well, so when we apply a product of x's to it, that's flipping a certain number of bits, right? Which is the same thing as, like we did with the errors, is adding a vector. Okay? And so when we add, so which vectors are we adding? Well, we're adding vectors that correspond to elements of the parity check matrix for C2. Which, remember, are vectors that are in the dual code to C2. So we're adding vectors in C2 perp. Okay? And we have a superposition over adding all possible vectors. So therefore, our code words are going to look like this. Sum over x in C2 perp, z plus x. Where, so let's call this logical code word z, where z is in C1. Okay? Now notice that in order to have a CSS code, we needed C2 perp to be a subset of C1. Right? I wrote that over there. And C1 is a linear code. So whenever we take this z in C1 and add in another element to C2 perp, we're getting another element to C1. Right? So this thing here is a sum over different elements of C1. But it's not all elements of C1. It's only elements of C1 that differ by an element of C2 perp. Okay? So so basically we're breaking this into, this is a sum over some coset of C2 perp in C1. Right? So we're looking at C1 mod C2 perp. Oh, it's the wrong place to write it. And so basically what this thing is labeled by is labeled by an element of C1 mod C2 perp. Okay? And that's actually the original way these CSS codes were defined. They were not, this was done before stabilizer codes. Right. And so if you work it out, you say, oh, well, how many possible such things are there? Well, C1 has K1 basis vectors, K1 elements, sorry, K1 vectors. No, K1 basis vectors. And C2 perp has n minus K2 basis vectors. So how many cosets are there? There's K1 minus n minus K2, which is exactly the right thing up there. K1 plus K2 minus n. Okay? So that's another way of seeing how many qubits are going to be. And you can see how this all matches up. Okay. Further questions on that? Yeah.
Quick question. Is there any way that K1 plus K2 minus n could be negative?
Well, so if you just take two arbitrary codes, C1 and C2, certainly it's possible, right? But when you have that constraint, C1 perp is less than or equal to is a subset of C2, well, that's exactly what this is saying, this argument is saying, right? By saying, and so in order for that to be possible, that means that K1 has to be greater than the size of C2 perp, which is n minus K2, right? And in that case, K1 plus K2 minus n is going to be positive. Now, I should say that if you happen to pick C1 perp and C2 such that, sorry, C1 and C2 such that C1 perp is actually equal to C2 instead of a strict subset, then this construction will still work, but as you can see from this argument, you'll actually get only one code word, right? So it'll be 0 logical qubits, which is kind of sort of an error-correcting code, but it's something you have to treat separately. It's more like, it's some interesting entangled state, some particular state that has some interesting properties. And it's obviously not useful for encoding actual information. Yeah?
C1 perp is subset of C2, is equivalent to saying C2 perp is subset of C1?
Yeah, because of this property, that the perp of the perp is equal to itself. Okay, so if we take C1 perp subset of 2 and we take the perp of both sides, that's saying C1 perp, well, okay. Yeah, okay. So the other thing you have to know is that taking the perp switches the order of inequalities. But yeah, it is equivalent. Okay, so anyway, the CSS construction is really helpful for finding stabilizer codes because there's this vast literature on classical coding theory, and all you have to do is you have to kind of look through it and say, oh, here's 2 codes that are dual, or one is contained, the dual of one is contained in the other one, and then I can just take them and make a quantum error-correcting code out of them. That's great. The problem is that CSS codes cannot be as efficient as general stabilizer codes. Well, that's one problem, but that's probably the biggest one. And so there are definitely going to be cases where we want to look at more general stabilizer codes. So for instance, this 5-qubit code I showed you, you can't do it as a CSS code. Right? The way I wrote it down certainly had x's and z's in each row, and it has to be that way. In fact, the smallest CSS code that corrects one error is this 7-qubit code up there. So that's a motivation to keep considering general stabilizer codes. Now, there are some cases where we know non-stabilizer codes can even be better than stabilizer codes, but the differences are much smaller. I'm not sure I know of an example where you can even get one more logical qubit by going to a non-stabilizer code. You can get kind of fractions of the logical qubit. So it does pay to have other ways of converting classical codes into quantum codes. Yeah?
Can you always use like the same code? Can C1 equal C2?
I mean, C1, so it's not true that, so for arbitrary linear code C, it may not be true that C perp is a subset of C, which is what you need for this to work. Right? The Hamming code, it is true, and there's some class of weakly self-dual codes that have that property. And so you can definitely get a very broad class of codes that way. Probably you can't get all codes of interest that way. I can think of at least some that you would not be able to, as far as I know. So certainly, I mean, so actually, I think when Calderbank and Shor defined these codes, actually they did that they used the same code for C1 and C2, whereas Steen, I think, did different ones. But nowadays, we do the most general version. Okay, so let's think about classical coding versions of kind of more general stabilizer codes. And now we're not necessarily just thinking of a way to convert classical codes into quantum codes, so that's probably the most applicable thing. But since it's supposed to apply to general stabilizer codes, we want them to basically be equivalent representation of these stabilizer codes. So the first one I'm going to look at is the symplectic representation. Okay, so so the first thing to notice, I mean, when I introduced stabilizer codes, I said, okay, we're going to pick elements of the poly group to be the generators, right? And the elements of the poly group are tensor products of I, X, Y, and Z with signs plus or minus 1. But if all we're interested in is, I mean, so certainly if you want to get all the details of the code right, you have to include all that information. But the thing you really care about is the ability to correct errors, right? Which errors can it correct, which errors can it not correct, or even just detect. And that's determined by commutation and anti-commutation. And the overall phase, plus or minus 1, doesn't tell you anything about that, right? It commutes, plus p and minus p commute with the same things and anti-commute with the same things. Okay? So what we're going to do for these next representations is we're going to ignore the phase of the generators of the stabilizer. Okay, and you can pick any phases you want. You'll get a quantum error correcting code that has equivalent error correction properties. It'll be a different code. It'll be orthogonal, in fact, to the original one. But it will still work to correct the same number of errors. Okay, so what we're going to do is we have the polys, and we're going to replace them by 2-bit binary vectors. Okay, so I is going to be 0, 0. X is going to be 1, 0. Z will be 0, 1. And Y will be 1, 1. Okay? And then so if we have a tensor product, we're going to put, so we have this line in the middle, because the thing on the left is telling us if we have kind of an X part, and the thing on the right is telling us if we have a Z part. And so the Y has both. And so we're going to keep that separation between the X part and the Z part. And so if we have a tensor product like this for the 5-qubit code, then we would write that as 1, 0, 0, 1, 0, and then 0, 1, 1, 0, 0. Okay? Does everyone see how that works? So the first column here is the first poly. The second column is the second poly. Second column for both parts, and so on. Okay. And so the reason to do this is that now, so for instance, if we have the rest of the 5-qubit code, we'll have cyclic versions of this. So it'll be a classical binary matrix. Well, it'll be a binary matrix, but it'll be twice as many bits, twice as many columns, but the same number of rows. Okay. And the advantage of doing that is that then it's, in some sense, a classical code, right? It's a 2n-bit classical code. Now, the properties we're interested in are a little bit different from what we are in classically. So in particular, we care about commutation and anti-commutation. And so what does that correspond to in this representation? Well, suppose we have P and Q. And so P will be represented by this 2n-bit vector AB. And Q is represented by CD. Okay? Then P and Q, so when do P and Q commute? Well, in order to figure out if P and Q commute, we can just look at this version and say, well, every time we have an x here, if we have a z here, that gives us a -1. And similarly, every time we have an x here, we get a -1 if we have a z here. So let's count up the number of -1s. Well, the number of -1s is going to be the dot product of A with D, right? That's the number of places where both this has an x and this has a z, where both of these have 1, plus the dot product B times C. Okay? And so this thing is equal to 0 exactly when P and Q commute. Okay? So this is called the symplectic inner product. So if you've seen symplectic products before, you might be a little confused because normally there's a minus sign in a symplectic inner product. And the reason it's not here is because at the moment we're dealing with binary vectors. And for binary, +1 and -1 are the same. Okay? But really it should be there, actually. And when we talk about QDIT codes, you'll see it appear, probably. Okay? So the upshot is that a stabilizer code, well, you can think of it as a set of commuting Pauli operators that form the generators. Or you can think of it as a set of 2 n-bit rows that have vanishing symplectic inner product. Okay? And so, of course, the property of distance, you also have to write it in this way. But you can do that. Usually, yeah. So that's another way to kind of use classical coding theory with a more complicated distance condition to come up with quantum error correcting codes. It's to say, oh, well, I'm looking at things size 2n, and I want them to be symplectically self-dual, and then I'll try to come up with stuff that has good distance when I apply the quantum condition to it. It's a little clunky, but sometimes it works. Okay? I guess one more thing I want to say about this is that if you also do the CSS construction and you write it in this way, it has a very nice form. So for CSS code, well, remember we have some parts of the stabilizer which are from the code C1, which are just z's, and some parts which are from the code C2, which are just x's, right? And so a thing that's just z's looks like 0 and then something. So the first part of the CSS code, if you write down the stabilizer, you write it as a matrix. And so the first part will just be, each row will just be 0 for the x's, and then a row which is going back in the other direction, where we took, remember, we got the quantum code by taking the parity check matrix and turning the 1s into z's. And now we're going back. We're turning the z's back into 1s. So we'll just get back the parity check matrix H1 here. Okay? And for the x's, we'll get back H2, but it'll be on the left. So for CSS code, the symplectic representation always looks like this. Okay? So are there questions on this? Do this in one forward. Maybe. Okay. Yeah.
So is there anything that we have lost by forgetting about the physics?
A little bit. So obviously we've lost the knowledge of exactly what subspace we're talking about. Okay. So another thing that we've lost Yeah, so when we talk about fault tolerance, you'll see that you can understand a certain sets of fault tolerant operations on codes by symmetries of the stabilizer. And kind of most of the work of understanding those symmetries doesn't rely on those phases. But in order to actually get it right, to actually be something that maps the stabilizer to itself, you have to get the phases right too. So you're losing a little bit there as well. Basically, I would say that kind of 95% of what you do, you can do without worrying about the phases. But then before you're done, you should put back in the phases and check that everything still works. Depends on exactly what you're doing. OK, so then the last thing I wanted to do today is a different representation that uses a little more advanced classical coding theory to represent stabilizer codes. So I could say that, I guess I could say one more thing about the symplectic representation, which is that the main time it's useful is not to import classical coding theory. It's for doing computations involving stabilizer codes. And the reason for that is it just converts all stabilizer stuff into linear algebra. So this is something that I really should say. OK, so in particular, if you have the product PQ, then and P corresponds to the vector V, Q corresponds to the vector W, 2 n-bit vector, then the product corresponds to V plus W. Right? So anything you want to do of saying, oh, is such and such a thing in the stabilizer? This is going to be another example, actually. So you have some element, some poly, and you might want to know, is it in the stabilizer? This shows up. This kind of question shows up a lot. So one thing you could do is you say, oh, well, I'm going to take all sorts of products of the generators to see if I can get that poly. But that's kind of a pain in the neck. You don't want to take products of all of them. There's exponentially many. Right. OK, that reminds me of something else I should have said. But if you convert it to the symplectic representation, then it becomes a linear algebra problem. Is this vector in the linear span of these vectors? Right? And so there's a lot of machinery to answer questions of that kind. So that's where the symplectic representation is very useful. OK, so the thing that I was reminded of that I should have said before is, so why do we actually want to use the stabilizer representation? Why is it better? So one reason it's better is that we can directly look at it and understand what errors we can detect and correct. Okay, because the condition works directly on that, whereas applying it to the code words and the standard basis representation is kind of a pain in the neck. But the other reason is it's a much more efficient representation. Right? If you have an n-qubit code word, each code word could be a superposition over 2 to the n different things. And so even just writing down one code word is already exponential in the number of qubits. And you could have 2 to the k code words. Okay? So that's a really big thing just to write down. Whereas the stabilizer, all we have to do is write down the generators. Right? And how big are the generators? Well, there's n minus k of them. And each of them is, well, 2n bits long, 2n plus 1 if you include the phase. Okay? And so that's, much, much smaller. Now, if you also want to write down the logical polys, which is not a bad thing because that'll tell you exactly what the code words are, which the logical zeros and so on, then that adds a few more. But again, you only have to write down the logical x and the logical z. Right? So it's still polynomial in n and k versus exponential in the original representation. OK. So yeah, so moving on. So another way of writing these stabilizer codes is using classical codes over finite fields. So in particular, we're going to use codes over the finite field GF4, which has 4 elements. So I don't want to go into too much detail about finite fields. Probably some of you have seen them, maybe some of you have not. But a field, so a group has a multiplication, it's closed under multiplication, it has inverses. A field has addition and multiplication. So in a group, the multiplication doesn't have to be commutative. Obviously, we saw that. In a field, the addition and multiplication do have to be commutative. They both have to have inverses, except, of course, 0 has no multiplicative inverse. Right? So, most of the numbers, well, OK. So the integers are an additive group, a group under addition. They're not a group under multiplication because, 1/2 is not an integer. The rational numbers and the real numbers and the complex numbers, they're fields. They have their groups under both addition and multiplication, and it commutes and all the properties that you know of. So a finite field is a field that only has a finite number of elements. All the examples I gave you had infinite number of elements. And so kind of the easiest finite fields are the prime fields. So Z2, the binary numbers, which we've been dealing with a lot, that's a field as well. Because 0 and 1, you can add and multiply them. You get 0 and 1 again. 1 plus 1 is 0, of course. But the next more complicated finite fields are fields that have other things in them. So GF4 is a finite field with 4 elements, which are 0, 1, omega, and omega squared. And so this is a field that has what's called characteristic 2, which means that it's kind of built on the binary fields. So if you have any element in the field, then you add it to itself, you get 0. Okay? And so the other thing about this field is that this omega and omega squared are defined so that 1 plus omega is equal to omega squared. And omega cubed is equal to 1. Okay? So these equations tell you everything you need to know about arithmetic in this finite field. So 1 is the multiplicative identity. So if you take anything times 1, you get itself. If you take omega times omega squared, well, that's omega cubed, and that's 1 again. If you take omega plus omega squared, what do you get? Well, omega squared is 1 plus omega. So omega plus omega squared is 1 plus omega plus omega. And omega plus omega is 0. So omega plus omega squared is equal to 1. Right? So that's an example of how you can figure out all this complete table of arithmetic. And so we can relate this to stabilizer codes by mapping these 4 elements to the polys. So in particular, we can say 0 and I. Maybe I should write this separately. So 0 corresponds to I, and 1 corresponds to x, and I'm going to let omega squared correspond to y, and then omega corresponds to z. Okay? And so as before, I'm going to take every poly and convert it into a vector. Before it was in the symplectic representation, it was a 2n-bit binary vector. Now it's an n, a dimension n vector over this finite field GF4. So for instance, that same operator x, z, z, x, I becomes the vector 1, omega, omega, 1, 0. Okay, so, and once again, when you do this, multiplication becomes addition, right? So multiplication in the poly group is addition over GF4. Yeah. Okay. So then in order to make this work, we need to again have something that corresponds to this commutation relation, right? So when the two polys commute, when we look at the GF4 corresponding GF4 vectors. So to do that, we have to define two more things on the field. So we have to use a conjugate. So the conjugate is going to be defined this way. It takes 0 bar to 0, and 0 goes to 0, 1 goes to 1, omega goes to omega squared, and omega squared goes to omega. So if you know a little bit more about finite fields, you know you can construct these. This omega is you're joining the root of some irreducible polynomial over Z2. And then this conjugate is just switching these two roots. Right? It's a third order polynomial. It has two roots, two non-trivial roots. No, sorry, it's a second order polynomial with two non-trivial roots, and you switch them. That's what this conjugate does in this particular case. And we also need a trace, which does relate to the trace of matrices in a way that I don't want to get into right now. It's not too complicated, but I don't have much time. Okay, and trace of 0 and trace of 1 are both 0, and trace of omega and trace of omega squared are both 1. And what this means is the trace is a way of going from this GF4 back down to the base field Z mod 2. Right? We always get a bit out. And that's going to be important because, well, so the commuting versus anti-commuting, that's a binary thing. Right? And so what that means over here is that we can say that P and Q commute if and only if this following symplectic product, trace of V bar dot W is equal to 0. Okay? That's just a calculation you have to do. It's not immediately obvious that this is right. Okay? But with all the correspondences that I've told you and these properties, this turns out to be exactly the case. So you only have to check this, I should say, for single qubits. And then for multiple qubits, well, this you're just adding it up. Well, yeah, basically all of these things are additive. So you're just adding it up over the different qubits. And that's the same as adding up the things here to count whether it's an even or an odd number of commutations. Okay? And so yeah, so then one last thing about this representation, which I've run out of space to do. So in order then to make stabilizer codes, you want to look at GF4 codes, and people have devised such things. But you want to look at codes that are weakly self-dual under this inner product again. And again, there's a slightly different error correction condition you have to worry about. But so one thing that's one distinction that's worth making. So when I was talking about binary codes, a linear code, it's gone, I guess. So binary code, a linear code was defined by being closed just under addition. But really, a linear code should be more than that. So linear code over GF4, so if you have two code words, and you have some element of GF4, so the scalar multiplication is going to come in, then that implies that x plus alpha y is in the code as well. Okay, so addition of code words is in the code, but also multiplication by scalars is in the code. So again, this thing will form a vector subspace of the vector space over GF4. Okay. So for binary, that didn't matter because the scalar multiplication was just by 0 or 1. But for GF4, it does matter. The thing is that in the quantum case, while multiplication here corresponds to addition, and the stabilizer code is closed under multiplication, when we go to the GF4 case, that means that the code has to be closed under addition. So it's an additive code. So an additive GF4 code just has the property that it's closed under addition. But a linear GF4 code has this additional property of being closed under scalar multiplication. And in the stabilizer code case, that corresponds to having some particular symmetry. Scalar multiplication is not quite as natural an operation. Because what does it do? Well, multiplying by omega takes I to I, that's fine. But it takes x to z, and z to y, and y back to x. Okay? So you're doing this cyclic permutation of the Paulis when you scalar multiply. And you're doing it on every qubit, because scalar multiplication affects every qubit. And so if you have a linear GF4 code, you have a stabilizer code that has this additional symmetry. And it turns out that there's some version of the 5-qubit code that does, in fact, have that symmetry. So if this is a linear GF4 code, so it has 2 rows in the stabilizer in the parity check matrix. But it's a linear code, right? So that means that 0, omega, 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 omega is also in the parity check matrix. And if we're thinking of it as stabilizer, that's a separate thing. Okay? So as a stabilizer, this would have 4 generators. So we'd have I, x, 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 but also I, z, 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 z. And then we'd have x, I, x, z, y, but also omega 0, omega, omega squared 1, which is z, I, z, y, x. Okay? So these 2 codes represent the same thing. Okay, when this is a linear GF4 code, this is the stabilizer code. And so you see this is also a 5-1 something code, and it turns out it's also a 5-1-3 code, which is equivalent up to some local unitaries to the one I showed you before. Okay? And one reason this is interesting is this 5-1-3 code, well, is a classical Hamming code over GF4. And it turns out you can so the Hamming codes are not just a 7-bit code I showed you, but a more general class of codes that has this property basically that all the columns, remember for the 7-bit code, is it still up there somewhere? Maybe not. So the 7-bit code had this property that the columns were all distinct. And in fact, they went through all possible bit strings of the appropriate length. And so for binary codes, you can easily write those down. It's a little more tricky for GF4 codes because they have to be not just different, but linearly independent But you can do that, and that generates a set of perfect codes that have this property that I mentioned before, that the number of error synchrons is equal to the number of possible errors. And so you can get perfect quantum codes in the same way by using these GF4 codes. So that's an example of the application of this GF4 thing. OK, sorry, that ran a little over.